So welcome everyone. I hope you are enjoying KubeCon so far. In this session today, we'll speak a little bit more about how you can improve your model deployments and reduce the cold start when you're scaling or deploying AI models on Kubernetes. Because it shouldn't take like 10 minutes for you to get your models up and running to do inference. I'm Tiago Reichert, Solutions Architect covering Latin America startups. And here with me, I have Lucas.
Hey folks, how are you doing? My name is Lucas Duarte, Container Specialist SA in AWS, covering ISV customers just like Tiago. And yes, yet another talk about AI, but we promise to you that we're going to focus on the infrastructure side of AI and how we can actually reduce the cold start period. Any of you here is deploying inference workloads on top of Kubernetes? Yes? No? Yeah, like few
awesome.
people, awesome. But if you are looking to get started, you can get started in a good way, right, Tiago?
Right,
so let's
get into it. So before we go into the technical part itself, I think it's important to just notice how the customer experience is important for our businesses. And latency directly impacts that customer experience. If you think about like a web page when you're trying to browse something or like to try to buy something in an e-commerce, if the page takes like 4 or 5 minutes to load, what will you do? I will probably go to the next page and buy it there. And there is a study that shows that 53% of people will go to another page if it's taking more than 3 seconds. And it's not just about seconds. Even 100 milliseconds can already influence your conversion rates by up to 7%, according to this study from Akamai. But Lucas, we are talking about latency, we are talking about customer experience. Why does this matter for the AI workloads?
Yeah, before we understand why is it matter for the AI world, I think we already talked about that we're going to talk how to reduce cold start. So it's essentially the time that it takes to deploy your inference endpoint on top of your cluster and the time that it takes for you to do the first inference request to your model. If we look at how AI has been evolving over the time, over the years, we can look into 2018 with BERT-based small language models. The number of parameters were very few, right? And more the time passes, more parameters the models are having, so the models are becoming more generalist. Maybe someday we're going to end up in a Terminator that James Cameron foresee in the future, right? But I hope that's not what's happening right now, but the more parameters that the model have, more generalist, essential that model can be. And then if you take, for example, GPT-5 in consideration, that model can have more than 1 trillion parameters. And then with more parameters, you require more storage as well.
So if you consider like storage requirements, let's take an example, like a 7 billion parameter model like Mistral. It can take up like from 3 gigabytes into like 20 or even more gigabytes in storage, depending on the precision that you are using for that model. But something will always happen. The more parameters you have in your model, the larger the model will be. So it can be from a few gigabytes in size, as you just mentioned, like 3, 4 gigabytes, up to a terabyte in size, depending on the amount of parameters you have. If you have, for example, 1 trillion of parameters.
And that is exponential, right?
Yeah.
But before we look even further, I want to introduce to you a friend of us who is here in the audience today, not right now, actually. His name is John Martinez. John Martinez is a leader at DevOps, a DevOps leader at Octane Retail. He has been running Kubernetes for a while now, but he is new into AI/ML workloads. You know, just like us, we are just getting started. John Martinez has been running rock-solid Kubernetes for the past 8 years, and guess what? He also has an IDP, and he doesn't have problems with upgrades. Yes, that is surprising. John was happy until his CTO, Mark, approached him with a brilliant idea.
Hey John, I saw a video today earlier in YouTube that if we use this model here, we can improve our conversion rates by up to 20%. So why don't you deploy it for us by the end of the day? Is like 5 p.m. okay for you?
5 p.m. to have the model up and running? Oh, hold on. There you go. Absolutely, Mark. We have been running Kubernetes rock solid for like 8 years. What is different than deploy a YAML file in a cluster and use a controller to reconciliate? I mean, it's going to be the same thing. It could not be so hard, right? So then John did this first trial. So John has a cluster, an EKS cluster with cluster autoscaler, and he has a default EBS configuration. So he has not improved the EBS whatsoever, the volume that he's using in the instance. He's also deploying as I said, a cluster autoscaler environment, and importantly, he's deploying a Mistral 7 billion parameter model. And if you look at the screen right now, here I have a K9s screen where we can look at the pods running in the cluster. Here we have an EKS node viewer so we can see the node scaling. And here is my cool UI that I built using, of course, AI, because the talk is about AI. So let's take a look how much time it takes to deploy John's first model into the cluster. So there you go, we are gonna click and deploy baseline. Baseline deploying is gonna get started. We can see that the pod ended up in pending state because we don't have enough capacity. Now cluster autoscaler is started to get triggered, and then we should be able to see a node coming up pretty soon. There we go, there is your node. Awesome, G6Z 2x large. Node spin-up time was 1 minute and 45 seconds just to spin up a node with cluster autoscaler. We're gonna understand that later today. Now, we are pulling the image. It took 3 minutes and 44 seconds to pull the image, and now is the time that we are downloading the model from Hugging Face and loading that model into GPU memory. Let's see how much time John needs to wait to load that model into GPU memory and download it from Hugging Face. And of course, these are the fastest 3 minutes of your life, but the demonstrations is speeded up. Oh my God, it took 14 minutes and 30 seconds to deploy your first inference workload on top of Kubernetes using cluster autoscaler without any optimization. That is John's face, right? So 14 minutes and 30 seconds, the customers are abandoning their carts while waiting for AI recommendations. But hold on, the model is just 14 gigabytes. Why is it taking so long to download and load into the GPU?
And then John realizes it's not just the container image size, it's the entire containers ecosystem that is the problem.
Thanks, Morgan Freeman.
You're welcome. So if you look into the models, as we mentioned before, it can be like terabytes in size. But it's not just the model size, it's also the containers. If we take VLLM as an example, it's more than 10 gigabytes in size. If you compare that to web applications that has just a few megabytes in size, it takes way longer to pull that container image into your workloads, into your instances to run your workloads. And if sum that up to other frameworks like Ray, Dynamo, and so on that you might be using in your environment, that can be a long time to pull those images.
Right, so John went back to his CTO and said, Mark, here's the deal, bro. It's taking 14 minutes and 30 seconds to deploy that workload. I'm not gonna able to deliver that to you at 5 p.m. because we're not gonna give a good experience to our customers. Can you help me since you are the CTO?
Right, I was actually expecting more from you, but I saw a LinkedIn post earlier today that Lucas and Tiago will be doing a presentation at KubeCon Atlanta. Why don't you show up there and learn something on how you can improve those model deployments?
Oh my God, hey John, welcome to the audience.
Nice to see you.
Nice to see you too. So let's break it down. He's not there, guys. Let's break it down, right? So before we break it down, I'm gonna ask Tiago to slice the architecture for us to understand how are the steps that we need to get an inference endpoint running in our Kubernetes cluster. So the first thing that we need is?
Guess what? A Kubernetes cluster.
There you go.
So after we have the Kubernetes cluster up and running, the next thing we have to do is probably have the accelerated hardware on which we want to run our models. In our case, we are using NVIDIA GPUs. And after you have the NVIDIA GPUs up and running, the hardware is there, you will have to have a way to load the model into the GPU. We can use something like VLLM for that. VLLM will load the model for you, it will have it ready on the GPU for you for doing inferences, and will also provide an endpoint, an API endpoint for you to do the inferences. But after you have pulled the container image from VLLM that we saw that is a few gigabytes in size, the next step is to download the model. And we can download that model from Hugging Face, for example, from the internet, and load it into the GPU. And when we have that done, we can have our users, agents, and applications consuming those models for inference. And soon enough, you might also realize that you also have to scale that inference. So the demand grows, and you have to have multiple instances for attending the demand growth that you have on your inference workload. So you have to scale your workload horizontally. But Lucas, how can we get started? Let's go in piece by piece.
And of course, since we work in AWS, John is running on top of Amazon EKS, so he has already the cluster, so the focus is not a lot on top of the Kubernetes, but he already has the cluster. What is the next step? He needs the accelerated instances there, right? But it's not just about the instances and the accelerated drivers. We actually need NVIDIA runtime, the right drivers, we need the device plugin to expose the GPUs to the containers, otherwise we cannot use them. So all that stuff needs to be there. So we need to define the operating system that we can use in our cluster. So in AWS, we have some good options that can also help you to improve the cold start period. And by the way, EKS optimized AMIs, you can use EKS anywhere, you can look at the open source repository, feel free to do so. But Tiago, what are those AMIs that we can use?
Right, Lucas. So if you're using AWS, we highly recommend you to use the EKS optimized AMIs. Why? because they already have everything pre-built to run as an EKS node, as a Kubernetes node, but not just that, also like the drivers for your accelerated hardware, such as NVIDIA GPUs in our case here. It has EFA adapters already installed, all the runtime installed, but there is something that is important also to take into consideration, that is Bottlerocket versus Amazon Linux 2023. Bottlerocket already has the device plugin pre-installed. So when the node spins up, you don't have to deploy the device plugin for your containers to have access to the GPU instances. That can also take some time. But stick to the end of the session and you will see how much time that actually takes.
Save that information for later because it's going to be important.
Yep. And we saw John was using cluster autoscaler to scale the cluster. That's fine. But there are other options, open source out there that they can use. For example, Carpenter. But Lucas, why should John maybe consider Carpenter to scale the cluster?
That's a really good question. Is there anyone here that uses Carpenter in production at scale? I mean, I already know they use Carpenter production, but good to see that people use that. But for folks who are not familiar with, let's understand how Carpenter works. But before talking how Carpenter works, we need first to understand how the scaling works on top of Kubernetes. So first, your application will scale out. Your pods will end up in pending state if the scheduler doesn't find any place to place those pods in. Once those pods are in pending state, then your good friend cluster autoscaler will be triggered. And the way that cluster autoscaler works is by changing the amount of desired instances into a autoscaling group definition. So in this case, you have the minimum max amount of instances. Cluster autoscaler will just change the desired amount of instances. And you cannot use different instance sizes and types, so that leads to a large proliferation of autoscaling groups, and it's harder to do upgrades as well. But after you are done with that, then you trigger autoscaling group will trigger the EC2 API to then provision that worker node for you underneath your cluster. And as we saw, John's deployment, it took 1 minute and 45 seconds just to have your node up and running. And why is that? Because as you can see, there's a lot of steps involved here. We have cluster autoscaler, we have autoscaling groups, and all of those steps will take some time to be executed. So what Carpenter, what we essentially are doing is we are removing cluster autoscaler and the autoscaling group of the equation. This is what we call a groupless auto-scaling mechanism, and then we are replacing that with Carpenter. And Carpenter, instead of talking to the EC2 API, is going to use the EC2 Fleet API, who is essentially instant.
But how much do we get by doing that?
Right, so stick to the end of the presentation because we're going to do another benchmark, and this is essentially to make you stay here to the end. But we're going to see how much time we can save in the end of the presentation. But another cool features of Carpenter, if I can say, just to give you a little bit of overview, is it has dynamic instance selection. So as I was saying, it will not lead to a large proliferation of auto-scaling groups because it will pick the best instance based on the amount of resources that you define for both CPU and memory of your workloads. And then it can also be cost efficient because it can fall back from spot instances to on-demand instances. It can have consolidation. You can consolidate even GPU workloads. So it's a pretty good thing that we can do. Great. So we're already talking about Amazon EKS.
There's an alarm.
Yeah, there's an alarm. There's a clock here ringing. I'm losing ADHD. It doesn't allow me to have this kind of noise near me, bro. There you go.
You should wake up.
Awesome. So we have Amazon EKS already running. We have the GPU workloads that we defined. We pick the AMIs that we want to use, and then we have defined that we want to use Carpenter. And then the next thing that we need is actually the image that we want to use. We need that VLLM image that John loaded from the official Docker Hub, but it took 3 minutes and 44 seconds. What can we do, Tiago, to improve the pull time? What are some of the techniques that we can do to improve the pull time to achieve a better pull time?
Yes, right. So as we saw, the container image, it can be like more than 10 gigabytes in size. So a few things you can do to improve that container image size is probably using multi-stage build. With multi-stage build, you can use an image to build your application and then just copy the required dependencies for the runtime into another image and use that image in production. So in such a way that you remove the build dependencies in the image that you will actually use to scale, making that image smaller.
Come on, bro. I already knew about multi-stage build. I mean, we are not in 2012, 2013, you know. That's been a while that multi-stage has been talking about. You're not surprising me. I waste $2,000 to be here at KubeCon.
Hold on, John, hold on. Have you heard about Sochi as well?
Sophie?
Seekable CI. It's an open source project from AWS that allows you to speed up the pull time of your container images. You can use it in two ways. One is parallel pull or lazy loading. If you are using parallel pull, what will happen is it will open multiple threads in your instance to pull the container image, the chunks of your container image parallelly. And that will speed up the time to pull that image. For lazy loading, what will happen is you will have a Sochi index that you have to create to be able to use that feature. The runtime will see that Sochi index and only load the layers that are required for your pod to start. So let's say just 2 layers are required for a pod to start. It will load those layers sequentially, and then your application can already run, and the other layers will be loaded lazily later on when they are required.
That's great, but when should I use parallel pooling and when should I use lazy loading?
Right, so parallel pool is nice if you need like most of the application layers at the beginning, because then lazy loading won't help you. And also if you have a high throughput storage available, because otherwise, as you will see soon, the bottleneck can be your storage and you won't get a lot out of parallel pool, like having multiple threads pulling the images for you. And lazy loading is nice. Again, if you don't need all the layers when you start up your application, and if you want to optimize your storage costs. But there's just one thing that is important to remember, that is, for using lazy loading, you have to have that Sochi index, you have to create that Sochi index and add it to your container images in your OCI repository, otherwise you are not able to use it. Parallel pool does not require that. And since we didn't want you to test everything out to see what happens, what doesn't happen, like with VLLM, for example, we did a few tests for you already. If you are using a different image, we highly recommend you to do the test by your own, but we use this VLLM image from the deep learning containers from AWS, and without Sochi enabled and a default DBS configuration of 200 gigabytes, 3K AOPS, 125 megabytes of throughput, that's the time that we got, 4 minutes and 20 seconds. And it's not just the time to pull the image. Here we're counting the time to inference. What's that? It's the time since we started to pull the image until the image is there, VLLM is running, and we are able to do inference requests.
And why is it less than the 7 billion parameters that we see? Because for this benchmark, we are using a 1.5 billion parameters. So for that reason, it's not 14 minutes. But all the best practices would apply in the same way.
We are not focusing on the model right now, we are focusing more on the container image. That's the reason why we have a smaller model right here. And well, then this enables Sochi. Let's try Sochi lazy loading. What we got is a 41% improvement on the time to inference. So pulling the image and have that model ready to do inference. Why do we not say the pull time here? Because it will take like 10 seconds, something like that, to the container to start. But we don't want to measure how much it takes for the container to start. We really want to measure how much time it takes for you to do something meaningful with that container. Therefore, we are measuring here the time to inference. If we compare, for example, with parallel pool, as you can see, not that much of an improvement. Why? Because probably the storage is our bottleneck in this case here. Lucas, what happens if we improve our storage?
Right, just by improving the storage, as you can see, before we were in 4 minutes and 20 seconds with Sochi disabled in a very poor storage configuration. Now, just by improving the storage in IOPS and throughput, we're able to get time to inference down to 3 minutes and 8 seconds without enabling Sochi. By the way, Sochi comes already on feature on Carpenter, and you can enable that as a feature gate. There's no additional configuration that you need to do in order to enable that, apart from adding the feature gates there. We tested lazy loading then with that EBS configuration. And then lazy loading was approximately time to inference 2 minutes and 19 seconds. So 26% improvement. And that's very similar to the other one that we saw, but we now have a much bigger and powered disk, right? So we can try parallel pooling. And this is where actually parallel pooling really shines, because since we have a really good EBS that has a good amount of throughput and good amount of IOPS, we can take the pool time, the time to inference down another 30% when we are talking about Sochi. Essentially, this is where Sochi actually shines. So we recommend you test lazy loading and parallel pooling. If you want to scan this QR code that's here on your screen right now, we have done a lot of benchmarks in a blog that we published with the CNCF to talk about in more details how you can configure that, but that's how you can improve the pool time. Again, we are not measuring just the pool time here because lazy loading or pool time would be like 8 seconds, right? But you need more layers to start. So you can try and see which one fits better your use case.
But you have to make sure if you are using like parallel pool that your CI repo is not throttling you, because you are opening like multiple threads and trying to download that image as fast as possible from your OCI repository. If that OCI repository is throttling you, you won't see the benefits of parallel pool. So it's important to notice that when you are choosing your OCI repository.
You might see something like go away. So if you see something like that, you're going to need to make sure that you have your own internal OCI to use with parallel pooling. But it's a really good thing that you can do to reduce the pool time of your images. So what is John thinking right now? That's nice. So we're talking about the cluster, Carpenter, Sochi to pull the image, but hold on. I think we're missing the most important thing. We are missing the model, right? We are downloading the model from Hugging Face before and then loading to the GPU.
The model is even larger than the container image, no?
The model is larger than the container image, you're right. So what can we do to improve also the model load time into the GPU so we can reduce even further the cold start times? Tiago? Actually, it's not Tiago, that's me. Oh, awesome. So we're gonna talk about storage services. Essentially, instead of us downloading the model from the internet every time that we need to spin up a new replica, we should have our own internal registry or repository or whatever you want to call that, because people use terms like those interchangeably, just like platform engineering and SRE. So in AWS, we have block storage, we have file-based storage based on a networking file system like Amazon EFS, FSx for Lustre, and also we cannot forget object storage like Amazon S3. So in order to pick which storage is the best one for our use case today, for John to impress Mark, so Mark can be happy with him, we have done some benchmarks, right?
Right, Lucas. So if we just taking the model from Hugging Face, download it from the internet, if we just improve the EBS storage throughput, as you can see here on the bottom of the presentation, like this, the configurations that we did, we already went down from more than 500 seconds to 152 seconds to pull the model from Hugging Face and load it to the GPU. But as Lucas mentioned, maybe we don't want to do that over the internet all the time when we have to scale our workloads. So what we can do is, for example, use EBS. We tried EBS with CSI driver, and we were able to get down to 78 seconds with the optimized EBS with more throughput. But we didn't stop there. We did a few additional tests. We tested EBS with pre-pool. And by pre-pool, what we mean is we have an init container that downloads the model from the EBS using the CSI driver into the local RAM, and it does that in parallel, opening multiple threads. So again, taking advantage of a high throughput EBS, as you can see here. And we were able to reduce the time it takes to pull the model, and then afterwards VLLM to load that model from the RAM into the GPU down to 29 seconds.
But EBS, if I'm not mistaken, we cannot mount EBS in different availability zones. So essentially, if we're scaling up your replicas and worker nodes, we're gonna need to have the models locally there somehow. So I don't think that's the best storage service that we can use here, right?
Right, so probably you don't want to copy the model over and over and maintain that updated across multiple volumes. You could use something like FSx for Lustre. It's a volume that you can mount across multiple AZs. And now you don't have to replicate this across AZs if you have your workloads running on those AZs. The pull time for FSx for Lustre was 110 seconds for that same model, and it's also important to notice that this model is around 20 gigabytes in size that we are using here, the Mistral NeMo Instruct, but we also did a few optimizations here. We tried to strip the model at FSx size, so we have more IOPS on the FSx volume side, and we also used RunAI, that is an open source project, to pull the model in parallel and load it directly into the GPU in parallel. With that, we were able to go down to 46 seconds.
All right, but FSx, I'm gonna need to set up FSx, and we are using it at object storage, right? And I mentioned before that we can use S3 for that. have we done any tests on S3?
Right, so I think it's really important also to notice about the S3 because it's probably like the most cost-effective option for you to store your models, at least on AWS. And if you consider, for example, Amazon S3, we use the MountPoint CSI driver to install in the Kubernetes cluster and access those S3 objects, and we got a time of 22 seconds to load that model into the GPU. We also tried with Run AI, and we got the same time. But the nice thing about using Run AI is that it already comes pre-built into the VLLM container image, so that you don't have to install any add-ons and maintain any CSI drivers just to access the model. VLLM can directly access that model on S3 and download it and load it into the GPU for you. And it took 22 seconds. Just like for your information, in this instance here, we were maxing the throughput of the network. That was our bottleneck in this case to be even faster. Now we have the entire cluster created. We have the Kubernetes cluster, the instances, VLLM pool, using Sochi. We have the model also loaded using S3 and Run AI. We have our applications and agents using this application.
Oh, hold on. John is leaving the room right now. Bye. And now he's gonna sit on the floor like we all do, and now he's gonna test if it actually improves the first performance. If you remember, it was taking 14 minutes and 30 seconds without any optimization, and because John is too excited and too anxious, he cannot wait to be at his office to do all those tests, so he's seated right there like, yeah, I think so. Awesome.
I see his head.
Yeah, so like he's streaming the screen right now. So let's see how much time it's take right now. Just to give you a wrap up of what is the setup of the cluster. We have a EKS cluster set up with Carpenter. We have Sochi enabled with parallel pooling. We are hosting the model on Amazon S3, and then we are using Run AI model streamer to load directly the model from S3 using multi-part download. And as soon as we download the chunks, we load into the GPU. So let's see how much faster John can get this model deployed to impress Mark. So there we go. Optimize it, deploy it, up and running right now. We should see a pod coming up in pending state here pretty soon. Of course, there you go. The pod is in pending state. After the pod is in pending state, as you can see, we have a node already started to be registered in our cluster here. So now is the time that Carpenter is doing the node provisioning. Let's see how much time it takes. 51 seconds to provision a node compared with 1 minute and 45 seconds that we saw before. Now we are pulling the image with parallel pool enable. Let's see how much time it takes. 1 minute and 16 seconds compared to the 3 minutes and 44 seconds that we saw before. And now we have the model load time that we are using Run AI model streamer directly from S3. Let's see how much time it takes. It's loading chunks, as you can see right there. There you go. So in a few seconds, we should see the total time that it took to do the complete cycle in a fresh created instance. So from 14 minutes and 30 seconds to 3 minutes and 11 seconds in a freshly created instance. That's the sound that he has done because of that, right? So, I mean, now I'm ready. I think Mark's gonna be super happy, right, Tiago?
Hold on, John, you are too excited. Let's see a few other optimizations that you can do. For the sake of time, we are not able to cover everything here, but remember that I mentioned about Border Rocket at the beginning of the presentation, that you don't have to install the device plugin. By doing that, we also got a few additional seconds here, like from 52 seconds to 39 seconds. And if we compare, for example, the improvements that we got from all the optimizations that we said during the presentation, it's like 77% faster to have your models ready for inference. And if you use Border Rocket in the tests that we did, we were able to improve by another 22% the time for inference. But this is still not everything. As you are scaling your workloads horizontally, like having distributed inference, you might want to look into things like KV cache, smart KV cache-aware routing, so that it routes the inference request to that instance that can best answer that specific inference request if you have like multiple instances with the same model. Prefill decode disaggregation, and even like KV cache offloading, so that it offload the KV cache from the GPU into the CPU memory, so that you have more GPU memory for the model itself. There are a few frameworks out there, for example, Dynamo from NVIDIA, Ray, or AI Bricks that you can leverage to have your distributed inference managed in a better way.
And next steps, all those QR codes have all the implementations that we talked so far. In the middle, we have a blog post, again, that me and Tiago published. We just have 45 seconds. So if you want to check this QR code, take a picture now, because we're not gonna let it a lot of time on the screen because we don't have more time. And then pictures, otherwise we can talk outside as well. So thank you so much, folks. We really appreciate your time. And look at John, he's so cute. So he's asking you to fill this set for us. Even if you didn't like this session, it's important for us because we can do better in the following one because we never give up. So thank you so much, and it's very good to be here with you.
Thank you.